This lesson focuses on Lewis structures and some different kinds of bonding associated with these structures. The basics of bonding in chemistry is credited to Gilbert Lewis. And Gilbert Lewis is an American chemist who took all the evidence at the time of chemical formulas, valence electrons, octet rule, and also the electron shell model of the atom, so the Bohr-Rutherford model, to try to explain chemical bonding. And he did a pretty good job, right? We know that bonding is one of the most theoretical concepts in chemistry. We cannot see atoms, we can't see electrons. We can only theorize what the electrons do and how they bond based on properties of all of the compounds that exist. So Lewis's work gave us some, clear understanding of bonding, but he focused in particular with covalent molecules and covalent bonding. And his structures were created before the development of quantum mechanics, but a lot of the basic stuff that he developed or ideas that he came up with still hold true today. So there are some key ideas of the Lewis theory of bonding, and many of these are not going to be new to you. You have learned these in your previous courses. So atoms and ions are stable if they have a noble gas-like electron structure. So typically with noble gases in their outer energy level, they like to have 8 electrons. And so we call these 8 electrons a stable octet. The one exception there would be helium, because helium only has 2 electrons. But typically we say that they want to have 8 electrons. We know that electrons are most stable when they are paired. We understand that they spin around in opposite ways. They develop a magnetic field around themselves. And so once they are paired up with opposite spins, that magnetic field is locked in, really hard to break apart. Atoms form chemical bonds to achieve this stable octet of electrons. And the octet could be achieved by an exchange of electrons between metal and non-metal atoms, which we know is an ionic bond. Or the octet can be achieved by sharing electrons between non-metal atoms, which we know as a covalent bond. So what we'll do now is try to see a little bit of the overlap between the quantum model and electron configurations with Lewis structures. Because again, even though Lewis structures were created before the quantum model, there's still a lot of good things happening there between the two methods of bonding and showing electron placement. So let's write out the electron configuration for silicon. So silicon would be 1s2, 2s2, 2p6, 3s2, and then silicon sits in 3p and it sits 2 electrons in. And when we draw the Lewis structure for silicon, we know that silicon is in group 14. So if he's in group 14, he only has 4 valence electrons. And this actually still makes sense to us, because if you look here in this outer energy level of number 3, there is a 3s2 and a 3p2. So you have 4 electrons there in that third energy level, and those correspond to the electrons that we see for silicon. Similar, we can do something for oxygen. So oxygen's electron configuration is 1s2, 2s2, and then 2p4. And when we draw the Lewis structure for oxygen, he sits in group 16, and we put 1, 2, 3, 4, 5, 6 valence electrons. And when we look at the second energy level, there's 6 valence electrons there. And if we expanded our 2p orbital, so 1, 2, 3, and we put 4 electrons in, what we notice, there's our first 3, there's my 4th that's paired up. I have 2 unpaired electrons, and we notice that down here in the Lewis structure of oxygen. So jot down the electron configuration and the Lewis structure for the rest of these and try to see if you can notice a pattern between the configuration and the Lewis structure. So hopefully you've had a chance to jot down the configurations in the Lewis structure, and you should notice again that any unpaired electrons, you're going to see them here in the electron configuration that in some arrangements. So there's the 3 for phosphorus, and as we go through, bromine is a little interesting. So those 7 valence electrons actually come from the 4th energy level. Okay, so the 4s2, the 4p5, not the 3d10. So we notice that. This is really the only overlap we're going to start to see with quantum mechanics. Otherwise, we're going to just stick to Lewis structures for doing some basic bonding. So you've seen bonding for 2 or 3 years now. I want you to take a look at the valence electrons around each of these elements, and I want you to draw a Lewis structure. And go a step further and come up with the polarity of the molecule as well. Stop the video, try this, and when you've had a good attempt, keep playing and you'll see the answers pop up. So here are the Lewis structures. Hopefully you had no issue getting those down. And let's take a second and come up with the electronegativity values for all of these, because these are all covalent molecules. So the difference in En between a hydrogen and a fluorine is 1.43. This falls into our polar bond category because it falls within 0.5 and 1.7. There will be a movement of electrons towards the fluorine. And because you only have one bond in the molecule, that's your overall dipole as well. So it's also a polar shape. For nitrogen, if we're bonding it to itself, this is pretty easy. This is a difference in electronegativity of 0. So we have a nonpolar bond, perfectly shared electrons, and we have a nonpolar shape. When we bond oxygen and fluorine, we get a difference in En of 0.54. This falls into a polar bond, although it's not overly polar. So again, there's some pull of electrons towards fluorine, but it's not that great. And because there's nothing to counteract that pull on this side, we end up with a dipole through the molecule. So just a reminder, this will be polar shape. So just a reminder again of how to determine polarity, because this is an important concept and we have to still remember it even as we move into some different kinds of bonding. Now, the previous examples were typical Lewis structures where the atoms were trying to get 8 electrons, like a noble gas, by either sharing our electrons in our case, or, if it's ionic, then transferring electrons. But there are exceptions to Lewis structures and the octet rule. And the first exception is when we have an expanded octet. So we actually have more than 8 electrons around the central atom. And this tends to happen in elements of period 3 and higher. So here's an example. And when we see PCl5, it's a clue right away. You're trying to bond 5 chlorines to a phosphorus. So phosphorus has 5 valence electrons. And we know that 2 of those valence electrons are actually paired. So we come along with chlorine, who has 7 valence electrons, and we share right there. We share, that's supposed to be chlorine. We share to the other single right here, and we share on the other side with the other single electron of phosphorus. But I have to fit 5 chlorines in. And we know that this pair of electrons right here, there's an attraction, a magnetic attraction. But that magnetic attraction could be overcome by pressure or temperature. And so in some cases, it's not always the easiest option, but we can split those electrons and we can bond those chlorines right in to our phosphorus. And so we clean this up and we draw our phosphorus with all of the bonds as straight lines. And I now have 5 regions of electrons. So I want to get those bonds and those regions of electrons as far away from each other as possible. So we'll set up something like this. And don't forget, you should have all of those little electrons around your chlorines. And here we are with 10 electrons around the central atom as opposed to 8. Here's another example, xenon tetrafluoride. So xenon is a noble gas, and you're thinking, like, how does that work, right? So xenon has 8 valence electrons. He's a noble gas. He's stable. But we can still force those electrons apart. Again, it's not normal. And we can put in some fluorines. So if you are going to separate a pair, you have to bond both sets of single electrons. Okay, so we have to bond that one, and then we have to bond the one on the other side as well. You can't leave any single electrons. So if I bond those two, then perhaps I can bond these ones as well. So here come my 7 valence electrons, and we'll pair and bond those single electrons right there. So we got to clean this up. We're going to have our xenon here, and we've got, again, bonds to fluorine like this. And then we have our pairs of electrons also placed around my xenon. So it starts to look a little bit messy. It gets a bit crowded, but this is possible to have our noble gases bond and expand the octet. Conversely, you can have an incomplete octet. So you can have some elements where you don't get 8 electrons around the central atom. You get less than that. It tends to be in groups 2 and 13, but it's possible. So give these both a try. Stop the video, draw your valence electrons, pair them up, and then notice what kind of structure you get. So here are the Lewis structures for these 2 molecules. So boron trifluoride has 3 valence electrons. And once you share your electrons, you have to remember that you need to move the electron pairs as far apart from each other as possible. So those bonded electrons are repelling each other. So move them apart, and we form, the 3 bonds sort of in this triangular shape like we see. Beryllium is a kind of an odd metal. Even though he's a metal, it says there it does not dissociate into ions, and it tends to form covalent bonds. So beryllium has 2 valence electrons. We bond each of those electrons separately, and we move those bonded electron pairs to be as far away from each other as possible. And these are our 2 structures. Now, what do we do if we have polyatomic ions? So we can show bonding and Lewis structures for these, but they are a little bit different, and they need to follow a certain set of rules. So let's look at the sulfate ion, and the formula for sulfate is SO4 with a -2 charge. And what it says to do, number 1, it says position the least electronegative atom in the center. So that will be my sulfur, and then I'm going to just scatter my oxygens sort of around like that. It says determine the total number of valence electrons for all atoms. So I'll just number this step here. This is step 2. So I have 1 sulfur, which has 6 electrons. And so I have a total of 6 there. I have 4 oxygens, which also have 6 electrons. So that's 24. And then the thing you have to do here is you have to add on 2 electrons from the charge, okay? So right here, this charge on my polyatomic, I have to add that in. And then I get a grand total of 32 valence electrons. Step 3 says determine the total number of electrons needed for each atom to achieve a noble gas configuration. Well, our noble gases like to have 8 valence electrons, and I have 1 sulfur and 4 oxygens. I have 5 that would like to have 8 electrons. 5 times 8 is equal to 40. Now what we do, number 4, we subtract number 3, so my total over here, 40, from, subtract number 2, which is 32, from 40 to get the number of shared electrons. So 40 minus 32 is equal to 8 electrons shared, which means that I have 4 bonds that I need. Now, sometimes you can do step 5. I actually never do step 5. I find you don't need it. So usually here I'm good enough. I come over to my sulfur and my oxygens, and I put in my 2 electrons that will give me 4 bonds. So right there I have 4 bonds. And remember that we assumed everybody wanted to have 8 electrons. So I keep going and I keep giving everybody extra electrons until they have 8. So oxygen just needs 6 more and sulfur already has 8. I put square brackets around this because it is a polyatomic. I put the charge outside. And then if I count up all of my electrons, I should have a total of 32. And if you take a second and count up all the little dots in here, you should notice that you have 32 electrons. Let's try it again with carbonate. So carbonate has a formula of CO3 with a charge of -2. Number 1 says put the least electronegative atom in the middle. So I'm going to put carbon in the middle, and I'm just going to scatter those oxygens around. Step 2 says determine the total number of valence electrons. So I have 1 carbon that has 4 valence electrons, so a total of 4. I have 3 oxygens at 6 electrons, total of 18. And don't forget, in step 2, you have to add in the charge. So I'm going to add in these extra 2 electrons coming from the charge, and I get a total of 24 valence electrons. If I assume all of them in step 3 want to be like a noble gas, then that would be 1 carbon and 3 oxygens. That's a total of 4 atoms. At 8 electrons, that is equal to 32 electrons. And then step 4, I subtract those numbers off. So 32 minus 24 is equal to still 8 electrons shared, which means I need 4 bonds. Okay, so this is the way that we bond or show the bonding for polyatomics. So I come over to my structure and I have to put 4 bonds in there, and I only have 3 atoms of oxygen. So here goes 1 bond, 2, 3. So to get a 4th bond, somebody has to double up. So I'm going to double up right here. And now I've just made 4 bonds. And now I fill in the rest of my electrons, assuming everybody wants to have 8. So this oxygen that I just double bonded only needs 2 more pairs of electrons. He now has 8. And the other 2 oxygens need 6. And this is how we come up with the structure of a carbonate ion, and would give him square brackets and a charge of -2.